So hi everyone, I'm Yotam Lifshitz and I'm part of Itai Arad's group. And I will be talking about practical quantum statomography for Gibbs state. This work was in collaboration with Eyal Be'eri and IBM Quantum Haifa. So I will start by explaining what is quantum statomography. So think you have some unknown state of a single qubit row, and you want to know what is this row, and you have multiple copies of this state. So in order to understand which state do you have, what you have to do is to project the state into all the measurement bases, x, y, and z. And you have to measure expectation values in each of these bases. And then you have a full characterization of the state for the single qubit. The problem comes when we have multiple qubits and the number of measurement bases grows exponentially. To be exact, 3 to the power of number of qubits. And since we have to measure expectation value with multiple measurements in each such basis, this method becomes infeasible even for a small number of qubits. So there are few methods we try to address this problem. One, for example, with assumptions on the state, to assume that we have a pure state or some specific state that we are trying to tomography. And there are also methods we try to measure measure things without fully reconstructing the state, the density matrix. And the second part of the title was Gibbs state, so I will give a quick review. So the definition of a Gibbs state of Hamiltonian H with inverse temperature beta is the exponent of minus beta H with a proper normalization. And this state describes the equilibrium properties of the system with Hamiltonian H. And such states arise in many cases in physics, for example, the thermalization with heat bath, or the thermalization of closed subsystem, also known as the eigenstate thermalization hypothesis. And in other cases are half system near critical point, as stated in the Bizagonano-Wichmann theorem, which I probably mispronounced. And they are also used in quantum algorithms, for example, quantum Boltzmann machines in other cases. So as we can see, they are very common in quantum systems. So we would like to do tomography for quantum Gibbs states. So we'll start with a simple example. Say you have some Gibbs state of the transverse Ising field model, with the Hamiltonian defined here, with unknown J and B, sorry. And you want to know to do a full tomography of the state. So in order to simplify this problem, you may have an ansatz for your density matrix. Since you know this is a transverse field Ising Gibbs state, you may say that my density matrix is of this form with J tilde and B tilde, and I want to optimize this ansatz such that J tilde and B tilde will be eventually equal to J and B. So what we do is measuring some local observables, and we optimize the loss function, which is defined by the difference between the expectation values of the ansatz and the expectation values of the measured quantities. But consider a case where you don't know which Hamiltonian you have a Gibbs state for. You only know that you have some Gibbs state of a local Hamiltonian, but you don't know what are the terms of this Hamiltonian. So this is where our method comes to help. So we exploit the fact that rho in the case of Gibbs state, is a function of H. So there is a Hamiltonian learning algorithm proposed by Eyal Be'eri, Itai Arad, and Netanel Lidner that say that we can use a simple linear equation. Since rho is a function of H, then the commutation relation between H and rho is 0, which then leads, using the cyclicity of the trace, to the fact that the commutation relation between A and H for any operator H is 0. For any operator A, the commutation relation between A and H, the expectation value over rho is 0. But in fact, we'll only have some finite number of measurements, so the expectation value will be only something close to 0 because of statistical noise. And what we do is we are taking several best solutions to this equation, and we use them as an ansatz for the Gibbs Hamiltonian. We take several Hamiltonians which best satisfies this equation, and then we say that our ansatz is the exponent of some linear combination of these Hamiltonians. And then we optimize these thetas, or the coefficients in the linear combination. So putting it all together, we measure local expectation values. We solve the linear equation, which is much easier than the exponential equations. Then we make an ansatz of the best solutions to this equation. And finally, we optimize the thetas, or the coefficients of this ansatz, with respect to some local measurement loss function, as we saw before. So these are the results of our methods. This is a numerical simulations for a 5-qubit tomography of the transversalizing Gibbs states. As you can see, the green line over here is the traditional quantum state tomography fidelity of the reconstructed state. And these lines are the fidelity of our methods using different number of Hamiltonians in our ansatz.
What is M?
M is the number of measurements, So with only about few thousands of measurements, we get a very high fidelity with very small ansatz of about 10 to 20 Hamiltonians. Much higher than the traditional quantum state tomography algorithm. And this is also works for a higher number of qubits, for example, for 8 qubits, with only about 100,000 measurements and about 20 Hamiltonians in our ansatz. We reach a very high fidelity. The quantum state tomography is not even shown here because it's really infeasible for 8 qubits.
And again, what is L?
L is the number of Hamiltonians, or the solutions to the equations that we solve. H is the number of Hamiltonians in this sum, which we optimize the coefficients for.
So what it involves? Can you show the Hamiltonian? How many pairs? The interaction is between how many pairs? L?
Okay.
L is the number of pairs.
Yeah.
It's number of theta.
And this is the results on IBM quantum hardware, on the IBM quantum computers, and also for transverse fieldizing Hamiltonian Gibbs state. This is for 5 qubits, for which we found the ground truth with 5 million measurements quantum state tomography. And again, our method is much higher, has much higher fidelity than the standard quantum state tomography, with only reach about 0.7 fidelity. with only about 100,000 measurements. And we also tested it for 4 to 10 qubits, for which we cannot really do quantum state tomography and get the ground truth. So we compare with 3 local subsystems and measure the average fidelity between them and the quantum state tomography of them. So we can see that even for 10 qubits with only 100,000 measurements, we reach an average local fidelity of over 0.99. Thank you.